Welcome students. Actually, today we discuss about our chapter number 4, that is energy. Okay. Already this chapter is complete. Okay, because in your half yearly syllabus this chapter is also in your half yearly syllabus. And here also this chapter is in your pre-annual unit test. So today actually we discuss about the whole chapter energy, or we can say that we actually revise the whole chapter. Okay, energy very quick. Okay, now before knowing what is energy, actually you have to know what is work done. Okay, so first is what is work done. Okay, simply actually if we take a body like this is your body which mass is m and m is placed on a surface. Okay, and we applied a force F, capital F, from left to right side. Okay, and we want to move the body m, but body does not move. That means no work is said, no work done is complete. Okay, or we can say no work is said to be done. Okay, so what is actual definition of work done? The actual definition of work done, that actually if we apply a force F on a body M and body displaced, okay, from this figure from point A to B, and the distance AB is equal to, we take here S, then what is the work done? Work done, W is equal to product of force and displacement. Okay, that means actually if body is displaced along the direction of force, then we can say work is said to be done. Okay, this is your actual definition of work done. Now the question is, when we get no work done or zero work done. Okay, so that means actually if work done is equal to 0, suppose if W is equal to 0, we can say this is your 0 work done. Now what is the conditions? What are the conditions for 0 work done? Simply we get here actually three conditions. First one is when F is applied 0. Okay, so for this case actually we take an example that when we read a book, then there actually no force applied for this purpose, and we can say W is equal to 0. Okay, now we move to our next condition, when F is applied but S is 0, that means displacement is 0. Suppose if we push a wall for a certain time, okay, then actually after applying the force on wall, the wall is not displaced. That means we get 0 work done. This is one type of example of 0 work done. Now we move to our last point or last conditions, that is when angle between force and displacement is 0. That means we can say angle between F and S is 90 degree. Okay, here also we get W is equal to 0, because actually when suppose we take or pulley take a load on his head and move in horizontal direction, then the weight of the load is in downward. This is the direction of force and the displacement direction is in this direction. Here actually angle between load and displacement is 90 degree. For this purpose actually we can say Fs cos 90. Okay, here actual original equation for work done is W is equal to Fs cos theta. So you have to know what is the value of cos 90. Simply we can say here W is equal to Fs cos 90, and we know cos 90 is equal to actual value 0. In this case we actually get 0 work done. We take another example. When actually Earth is rotating around Sun, then the gravitational force act actually towards a center, and the displacement direction is tangent. Okay, so in this case also the angle between force and displacement is 0. So we can say Earth actually no work is said to be done for this case also. Okay. Earth actually does not complete any work done during its rotation. Okay. Now here we can say work is actually a scalar quantity. Now we move to our next point, that is what is the unit system. Okay, so here actually W is equal to, simply we can say Fs, okay, cos theta, but cos theta has no unit, so simply we can say in SI system actually unit is joule. Okay, that means actually force, what is the unit of force? Newton. And what is the unit of displacement? That is meter. So we can say 1 joule is equal to 1 newton into 1 meter. Okay, and what is its CGS unit? So for this case actually we can say 1 arg. Arg is the CGS unit of work done, is equal to 1 dyne into 1 centimeter, and dyne is the CGS unit of force. And we have to know actually what is the relation between Newton and dyne. We already know 1 Newton is equal to 10 to the power 5 dyne. Now if we use the relation, then 1 joule is equal to 1 Newton, that means 10 to the power 5 dyne into 1 meter, that is equal to 10 square centimeter. So we can say 1 joule is equal to 10 to the power 7 R. This is the relation between two unit system of work done. Okay, now actually we also take actually some more different unit, that is, or some large unit, that means 1 kilojoule, that is equal to, we can say, 1000 joule. Okay, if we take 1 megajoule, then we can say this is equal to 10 to the power 6 joule. But if we take 1 millijoule, that is equal to, we can say, 10 to the power minus 3 joule. Okay, or if we take 1 microjoule, then this is equal to 10 to the power minus 6 joule. Okay, now we actually know what is the energy. Okay, Simply we can say energy is capacity or capability of doing work done. Okay, and it has also the same unit of work done. That means for SI system actually unit of energy is joule, and we can say for CGS system it is actually R. Okay, now here we have to discuss there are actually several types of energy in our daily life or in our real life, but actually here we discuss about just mechanical energy. Okay, already you know in this category actually there are two types of energy. One is we can say potential energy, one is potential energy, and another one is kinetic energy. Okay, now the question is what is potential energy and what is kinetic energy. So in this case actually potential energy can store due to its change in position or change in shape or size, we can say. So this potential energy classified in generally two types, that is one is gravitational potential energy, and second one is elastic potential energy. Okay, what is gravitational potential energy? Actually gravitational potential energy, if we actually take a body or ball whose mass is m and this ball is taking to a height from ground surface, that is from which this is h, and body is placed this point, or we can say the ball is moved from A to B point. Okay, then here actually gravitational potential energy is equal to, we can say, mgh, because here actually force is mg, that is weight of the body, and the displacement is h. So here the energy, gravitational potential energy mgh, is stored in the body. And what is actually elastic potential energy? Generally actually elastic potential energy, and actually if we take a rubber band and we want to stretch or compress, or if we take a spring, so we actually made a compressed spring, or we actually stretched a spring. So in these particular cases actually we get elastic potential energy, and for these cases we get actually different numerical based problem or numerical based formula for gravitation, sorry, elastic potential energy. But actually for your syllabus this is not included in your syllabus, elastic potential energy. Okay, numerical expression, not the concept, just numerical expression for elastic potential energy, that is not included. But if we take what is kinetic energy, then what is the kinetic energy? It is simply for motion of the body. Okay, when body is moved or body is in motion, then the some energy stored in the body, this energy is called kinetic energy, and this energy is equal to, simply we can say kinetic energy is equal to half mv square. Here actually m is the mass of the body and v is the velocity. Okay, so velocity of body. So if we want to find out the kinetic energy, simply we have to use mass and velocity. That means kinetic energy depends upon two character or two quantity, that is one mass and another one is velocity. And for this case gravitational potential energy depends on mass and height. Okay, always g is constant for a certain place, and m and h is varied So if m is bigger, or we can say gravitational potential is energy is directly proportional to m, and height also, the height is calculated from ground. Okay, and also we can say kinetic energy, which is directly proportional to velocity also. Okay, square, actually we can say ke proportional to 1, sorry, k proportional to v square. Okay, so v square. Okay, now we have to move actually uh, the law of conservation of energy. Okay, so already we know what is conservation of energy. Simply we can say in our actually universe, what is conservation of energy. Okay, so actually in universe we can say there actually, for this law, or for this particular law, we can say the sum of total energy of all kinds always remains constant. Okay, that means actually we cannot create or destroy energy, just energy transfer or transform from one form to another, from maybe chemical energy to light energy to sound energy to mechanical energy, and etc. and so on. Okay, so we cannot create or destroy the energy, just energy transfer from one form to another form. Okay, so if we take a example of simple pendulum, there also we can say this is the position A, and if this is the position B, so here also we can say actually total energy at A point, total energy at A point is equal to total energy at B point. For this particular case, if we take A point as ground, then we can say for A case, for A, potential energy is equal to 0 and Ke is equal to maximum, and sum of energy is called total energy. And for B position we can say Pe, if B is extreme point, then potential energy is maximum and kinetic energy is actually 0. Why? Because at extreme point B, the velocity of pendulum is 0. So the kinetic energy is 0. And for A point, when body actually, the motion of pendulum is like that. Okay. So this is the motion. So at A point, actually the velocity of the bob is maximum. That is why we can say kinetic energy is maximum at A point. But total energy, sum of this energy plus sum of this energy is always constant. Okay. And what is actually power? Power is simply we can say work done per unit time. Okay. Just we can say power is equal to actually work done W divided by time. That means rate of doing work done is called power. P is equal to, we can say, W by T. The SI unit joule per second, that is simply we can say watt, and in CGS system this is arc per second. Okay, this is actually in SI system and this is actually in CGS system. If we know the work done and time, then we can say how actually we find out the power value. So from this case we can say P proportional to W and P proportional to 1 by T. So inversely proportional to time power. And if we place W with Fs by T, and we know S is displacement, T is time, and also we know what is called displacement by time, that is actually velocity. Okay, that means we can say F into B power is also is equal to force into velocity, because V is equal to S by T. And for this case, if we write down the SI unit of power, we can say we know what is unit of force, that is Newton, and velocity, that means meter per second. This is also the SI unit of power, Newton meter per second, that is actually same as joule per second, because Newton meters, that means joule. Okay, so actually this is the end of today's class. Okay, in the next class we discuss about some problems on the chapter, that is energy. Okay.